very much like when we did derivatives. We're going to look at antiderivatives kind of in much more the longer version of how you would do it. And a lot of calculus and a lot of mathematics beyond it likes to look at the sigma notation. In other words, it's trying to add stuff up. But when we're trying to add it up, like in the long run, it's going to be something that's infinite. For example, I could write sine and cosine as an infinite series if you'd like. But that's not normally how we look at it. We look at it via the unit circle and other methods. And when we try and find the area underneath the curve, which we've been doing with rectangles so far, we've been doing with, well, like 3 or 4 or 5 rectangles. Well, what we're going to end up doing eventually is let's just put in as many rectangles as needed, which would mean go to infinity with it, and that should give us the answer. And it will, and they do that via sigma notation. So we're going to do a little bit of a review of what it even means first, and then we'll start doing some problems together to show you how it would be done kind of longhand, and then I'll show you the shortcut. So very similar to what we did in derivatives, kind of old school and then new school. So this first one, because remember, what's sigma mean again? Sigma stands for yeah, sum, right? Especially when it's uppercase sigma. Those in stats may have seen lowercase sigma mean something different. So notice this I and that letter right there are the same. So it's telling us we're going to replace I with a series of numbers. So for example, this one here is basically saying put 1 in place of that and write it down. Okay, so 1. And then what we're going to do is put the next integer in. The next integer would be 2, and you put it in there. And again, the sigma tells me to add them. And then we'll put the next integer in. Well, this could go on forever, as you can see, but luckily this particular one told me when to stop. When I substitute in 6, that's when I should stop and then add them up. So we substitute in 3, and then if we substitute in 4, we get 4. We substitute in 5, we get 5. Substitute in 6, we just happen to get 6. And so now what we would do is add them up. So we got, what, 10 there, 10 if I put all those together, so 21. Okay. Now, of course, there's probably a little bit quicker way of getting to that answer, and we're going to look at those as the days goes on. You know, how could I do that? Okay. How could I find that answer a little quicker? And in fact, we might even get to that one today. We'll probably come back to this example and do it another method. Okay. So this one here, oh, notice now I have squared it, and now it's a letter J. But that's okay because the letter down here is also J. So whatever letter is in there is what you're going to replace. So what if there are other letters in there? Will I be replacing those letters? No. Okay, the only letter I can replace here is J because that's this leading letter down here. Okay, is J. Now you don't notice now you don't have to start with 1. You can start with 2, and that's exactly what it tells me to do. So let's substitute in 2. So is the result just 2 like it was last time? No, when you substitute in 2, now the result is actually 4, right? And then you have to substitute in 3. And then the result is 9. And then we substitute in 4. And the result is 16. And then we substitute in 5. The result is 25. Should I substitute in 6 like we did last time? No, why not? Because, yeah, it's telling me to stop at that number. And so now we would have to go and add these. So I'm looking at it being 20, right? So that's 20 so far. And then that there is 34. So 54, right, is the total. Question so far. Pretty general idea of how to do that. Okay, but that's definitely more the longhand way of trying to compute these answers. So what do you find different about this one? Yes. Okay, there's no I. Well, yeah, that's just my typo, but yeah. Yeah, this is supposed to be a K down here, and it's not. So fix the typo. It's K equals 1 down at the bottom, so I apologize for that. But very good. I wasn't just trying to trick you there. That was just me messing up. Yes? Yeah, there's N at the stop, and then there's this weird N in here, which doesn't match the K, and just a lot of weird stuff, right? So when I substitute in things, am I actually going to substitute things in for, like, that N that's down there? No, I'm only going to substitute things in for k, right? So the best we can do right now is say to ourselves, well, if I substitute in the first one, so let's get rid of some of this so you can actually see what's going on. So again, down here, this is k equals 1. Well, I'd have a 1 over n, right? Just sitting there. I'm not going to substitute anything there. And then we would put 1 in for k. So put 1 in there. Right? So in other words, this would be, I don't know how you want me to write 1 squared plus 1, or do you want me to put 2, or just put 2? Okay. Plus, well, then there's going to be a 1 over n again. And then I would put in 2. And so it'd be 2 squared, which is what, 4 plus what's 5? Everybody good with that? Now, how long would I be at this? Truly, yeah, forever, right? So to let you know how it would end is we normally say we'll do this every once in a while. We put plus, and then we put the ellipsis, which is 3 dots. Then we're going to put plus, and then this would be the final one. But what would actually be the final one? Very good, n squared plus 1, right? You put n in, right? This is when I'm told to stop. Agreed? Putting n in. So it would be n squared plus 1. Can I do any better? Not really. About the only thing I could do is factor out the 1 over n, because they all have it, right? But other than that, is that really going to help me a whole lot in finding this answer? Nope, not unless they're going to tell me what n is. Okay. If they tell me that, then I can try and finish this problem. But you realize, even if they tell me n and I substitute it in there and there, is this answer right here going to be the sum of all of them? No, it's just going to be that term, right? Okay, so do you see how that could be a problem? Okay, so what we're going to look at today, now that we've kind of reviewed what this even is trying to have us do, is, well, what if they did get very general with this? Or they gave me various things for n? Or what if they made n 10,000? Do we really want to sit there and put all those in? Probably not. We're going to try and find a way to make that easy. Okay, well, if you want to, go right ahead, but I'm going to choose not to. Okay, so apparently I skipped some things here. But down at the bottom, did I not even write them on here? I guess not. I just jumped to some examples, apparently. Oh, well, that's not very nice. Are they down here? Oh, yeah, well, we'll write them down. One of them is this. Yeah, I'm not sure I even need to write this one, but I will. What are they basically saying here? It's like, yeah, I'm going to substitute I into that function, correct? And what they're saying is k basically has nothing to do with this, correct? So what, basically we just learned it in this last problem. What can I do with the stuff that has nothing to do with it? Just factor it out front, right? Couldn't I have done the same thing here? They're saying just go ahead and put that out there because it has nothing to do with any of the rest of it, right? Okay. Right? Pretty straightforward, right? And then the second one on your notes, again, you're going to want to get really good at reading this stuff on your own. What's it saying? That if I am putting 1 into some function plus or minus some other function, what can I do? What is it telling you? Just in your own terms. Yeah, you can split it up, right? Does that make sense? Some one of them, some the other one, and wouldn't they come out to the same sum overall? I'm substituting the same numbers, right? Okay, so that could be time saving. And now for the big ones that I'm going to have to write here, but it's on that little slip of notes that you have. What do you suppose the C stands for? This is number 1, right? What do you suppose that C stands for in this one? A constant. So in other words, is this one of them that we can do by hand? Now it's saying substitute 1 in there. What do I get if I substitute 1 in there? I get 4. Substitute 2 in there. What do I get? Substitute 3 in there. What do I get? And I stop, right? Because it says to stop at 3. So the answer is? So what is this rule saying? Yeah. Yeah, basically it says take these two and multiply them. Do you get the same thing? Yeah, that's a pretty straightforward one, right? Okay. And the one we're actually going to use on this particular problem is this one. They're saying that if I want to find the sum, I can just do that. Oh yeah, that one should look somewhat familiar from advanced math. That's the arithmetic series formula. Okay. And we did this problem before, right? The first 100 positive integers I should add in there. Positive. Okay. Remember how Gauss did it? 1 and 100, 2 and 99, so forth and so on, and added them up. So this formula would work here because I'm just going to put in 1, and then I'm going to put in 2, and put in 3, and put in 4. So that would work. So n is just this top number. So really the problem I have right here is that, correct? I could write this problem like that. Say put in 1, then put in 2, then put in 3, so forth and so on, right? So it says take n times n plus 1 and divide by 2. Well, what's n? N is 100. So 100 times 101 divided by 2. So is this going to be just one of the terms along the way, or is that going to be the total sum? That's just flat out the sum. Well, that's kind of nice. So if we do the math, it's basically 50 times 101, or a number that we've seen before. What? 5,050. And then you have 3 and 4 on your little sheet of notes there for what the summations of those would be, right? Those shortcuts for those. Okay. How are we doing? Questions? Okay. Well, that might help you. This one, let's see. If n was 10, is this one of them we could do on our own? Yeah, we could just write that out by hand, right? How about n being 100? Yeah, I probably don't want to do that, huh? 1,000? Yeah, 10,000? Yeah, we probably don't want to write out that many terms, right? So what I would do is let's do some algebra on this thing so that we can figure out this answer. I'm going to write it down again. Well, I'm going to just manipulate it as we go. Do you see anything of those algebra rules that we had before that might save us some time? I know I'm substituting in for I. Am I really substituting as far as sigma is concerned? I'm just going to do this in very general form so that I can get to something that I can just substitute n into, and it's just going to give me the answer. Okay? Because really, this sigma notation that we have over here is only substituting in things in for I, correct? Not for n squared. I just chose some arbitrary n's up here, correct? Yeah. Yeah, that's what I would do. Let's take that out, because isn't that what we do with that k on that other example, right? Put the k out front. So it turns into that. And we might want to put like brackets around it so that we know it's all getting multiplied by that. Anything else we could do to make this a little easier? I still see sigma. If we could get rid of that, that'd be great. But unfortunately, I think to truly get rid of it, we're going to have to create another one first. Perhaps you'll see why. What's one of those other rules? What does it say I can do? Yeah. Very good. If we're adding several ones, and that's all we're doing is adding them, we can separate them, right? Well, let's do that. We're adding right there. Well, let's separate those things. So it's sigma from 1 to n for I, plus sigma from 1 to n for 1. I don't really know why I changed to green there, but I did. It'd be wonderful if I could get rid of sigma and just put n in, right? So in other words, get rid of the i's and all this other stuff. Well, we got this 1 over n squared kind of hanging out here, and that's doing just fine. Do I know either one of these over here that are written in green? Do we have rules for either one of those? We do. In fact, we have rules for both of them, right? So this rule, the one on the left, is the one we just used in the last problem, isn't it? That's exactly the one we used in the last problem, which is n times n plus 1 all over 2, right? So is everybody clear that this one in green here is turning into that, and that's just going to give me the sum flat out. No other work, right? Plus, well, which rule am I really following for this other one? Yeah, the c times n, which I think is the first one on your little slip of paper, right? The one that says 1 to n of c is cn, that one, right? And our c happens to be what in our problem? Our constant happens to be 1, so it's going to be 1 times n, and n happens to be, well, n, so we're going to write n. Could. Depends on how you want to do it. A common denominator probably works. So to get a common denominator, 2n over 2, right? Would it be okay if I take that 2 and put it out with the 1 over n squared at this point? That's on the bottom. So it would be that. Right? Can you do that? Yeah. And then what do we got left in there then? I'll slow down. I see a lot of people writing here. Why are we doing this, kid? So that I can turn around and just put those n values in, right? Yes, question. Oh, yes, what do we got? Okay, can you FOIL that? Can you multiply that out for me or not? N squared, yep. Plus n and then plus close 2n, right? So is everybody okay with me writing n squared plus 3n? Is everybody okay with that? So really, isn't that just over 2n squared? Is everybody okay? I just say forget about that stuff being outside now and just put it in there. So is this just going to give me one of the terms along the way, or is that going to give me the sum? It's going to give me the sum. Does it matter which n value I put in? Not really. It's going to tell me the sum no matter which n value I choose. And it just so happens I gave you several that I would like you to choose. And there's a reason for the ones I chose. Well, they're easy is one of them, yeah. But so it's 10, 100,000, 10,000. So over here we'll say, what if n is 10? What are we looking at? Is one of them one of them? Yeah. So n being 10, what do we got there? We got 130 over 200. Maybe you're in agreement on that one. So in other words, 13 over 20, which in decimal form I'll tell you is 0.65. And being 100. I'll help you out here because I think this is all calculations we could all do, correct? I think we could all handle this. And there's more of a point here that I'd like you to see. Leads to 103 over 200, which is 0.515. It's a simplified form. I apparently have broken it. I keep missing it, that's why. Definitely got to orientate the board. All right. So now n being 1,000, I'll just give you again its simplified form. 1,003 over 2,000. You're probably seeing some kind of pattern here. 0.5015. And n being 10,000, you end up with 10,003 over 20,000, which is why do you suppose I had you do so many values and kept them increasing?
Correlation.
What correlation? Okay, that's part of it. What did I tell you we're eventually going to do with this sigma notation? We're going to find what's the limit as the number of rectangles, which is still related here eventually, goes to infinity. So did I keep making the numbers go up here? So what do you believe, as you look at these decimals, what do you believe the thing is if n goes to infinity? It appears as though this decimal keeps getting closer and closer to 1/2, right? 0.5. And let's just do our math from before and our work in advanced math. The limit as n gets really, really big. The top and the bottom have the same power. Correct? So as n gets big, something big squared plus 3 times something big. Yeah, who cares about that, right? As it gets bigger. And this is 2 times that same thing. So do you see the 1/2 that we learned in advanced math coming out? It's right there. And that would be the answer, as the limit as n goes to infinity is 1/2 in this problem. You don't exactly know what problem you just solved as far as calculus is concerned, but we'll get there. Okay. And then, as you show me you can do those, we'll do them together, and then I'll give you the shortcut. But that doesn't mean I won't ask you to do some, later on. I think you need to have the idea of the concept. Okay, any questions? No? All right.